Right, the main way that we calculate, or in a laboratory that we calculate the amount of heat that's released or absorbed by a system is using something called calorimetry. We briefly introduced it last time with physical changes, but it can also be used for chemical changes as well. We're going to go into more detail with calorimetry now. Calorimetry is a technique used to quantify the heat released or absorbed by a particular chemical reaction or phase change or any other physical change, really. A calorimeter is the equipment that is used for this analysis. There's a couple different types of calorimeters, so different types of calorimetry, but they're all used for the same general purpose. Some important quantities that you're going to need to measure that it's going to be given to you in your problem is the mass of the reagents that are involved in the reaction or the phase change, and then we need to have the mass of the calorimeter content. The calorimeter content, the things that are inside the calorimeter, that's the surroundings, and that's what we're going to measure. Then we want to measure the initial temperature of the content of our calorimeter and the final temperature of the content or whatever's in the calorimeter. Some essential concepts, knowledge that you have to understand this and to solve the problem right. You need to understand that the system is the reaction or process that's observed. The system is the reaction or process observed, and the surroundings are everything around that absorbs the heat produced by the system. Now let's emphasize this. The heat that's produced by the system, if it's exothermic, or the heat that's needed by the system if it's endothermic. Okay, so the surroundings are whatever can absorb or release heat to the system from the system. According to the law of conservation of energy, the heat of the system plus the heat of the surroundings, if you add them together, there's no net change. The heat of the system plus the heat of the surroundings equals 0. So the heat of the system has to be equal to the negative of the heat of surroundings. That's a really valuable and useful and important concept for solving these problems. If you know the heat of the surroundings, the system is the same exact value, except it's the negative of it. So it's the exact same number with a negative sign. In an exothermic process, the system releases heat to the surroundings. And if it releases heat to the surroundings, the temperature of the surroundings will increase. In other words, it'll feel warmer. In an endothermic process, the system absorbs heat from the surroundings. So that means the temperature of the surroundings, they have to give away some heat. The temperature of the surroundings will decrease. So it will feel colder. We cannot directly measure the properties of the system. This is an important concept, and I hinted at it a little bit when I said the thermometer is always the surroundings. You can't directly measure the properties of the system. We can only measure the properties of the surroundings. Usually they're the total mass of the content in the calorimeter, the initial temperature, and the final temperature of the solution. Those are the things we can measure, but it has to do with the surroundings. In this course, you can assume that the heat lost to the calorimeter, the thermometer, and other equipment is negligible. Don't worry too much about that. The general concept is we're going to assume that it's a direct transfer. The heat of the system is equal to the heat of the calorimeter, just the negative of it. Okay, a couple more things. With an endothermic process, this just kind of wraps it up and sums it up. Remember that the surroundings includes the thermometer. right? That's always going to be included in the surroundings. Just jot that down. So, in an endothermic process, heat is being transferred from the surroundings to the system. This is the direction of heat transfer. It goes from the surroundings to the system. The system is absorbing the heat. Surroundings give it away. So that means that the temperature will go down, or we could say delta T is negative. If it's an exothermic process, it's just the opposite. The system releases heat to the surroundings. That means temperature will go up and delta T is going to be positive. All right, the first type of calorimetry we want to talk about is soda can calorimetry or bomb calorimetry. Both of these cases we can assume that we have constant volume. Constant volume calorimetry is another way that you could refer to this. Keep in mind that the system, which is the reagents involved in the phase change, the reaction, whatever it is, and the surroundings are separated. Okay, so the surroundings will be the water and other spectator substances that are surrounding the reagents. But in this case, the system and the surroundings are separate. Let's look at the picture. Okay, so one example is a soda can calorimetry. Basically, you take a soda can, you fill it up with water, and you put a thermometer in the soda can. We would burn something under it, and we're assuming that the heat is basically transferred to the soda can. We know that some of the heat is actually lost to other surroundings, but for simplicity, we're assuming that most of it is transferred to the soda can. Well, we can't measure the system, so when we're determining the heat of the system, you measure the temperature change, the mass, and all the information to do with the surroundings. And we take the negative of that value to find out what heat was produced by the system. So when we're calculating, when the question asks you to calculate the Q of surroundings, we're going to do MC delta T. That is the mass of the surroundings. Okay, so basically the mass of the water surrounding the bomb calorimeter, or the mass of the water in the coffee can, or I'm sorry, in the soda can. Now, look down here at our bomb calorimeter. It's the same basic concept, except it's a lot more scientific. We've got this concealed container which does not change volume, and it's kept separate from the water inside the bomb calorimeter. So we have a closed container that we burn something in, and the heat is transferred from the container to the water that's surrounding it. So we're measuring the temperature of the surroundings. So the mass of the surroundings in the equation is going to be just the mass of the water that's outside of the bomb calorimeter. We've got an example next.